In this lecture, we will be discussing mainly a full adder. It's a construction of or realization of a full adder using a dual 4-to-1 multiplexer. Now, what is a 3-bit full adder? Now, a 3-bit full adder adds three 1-bit numbers. Often they are written as A, B, and C in, where A and B are the operands and C in is a bit carried in from the previous less significant stage. The circuit produces a 2-bit output. The output, carry and sum are usually typically represented by the C out and S, where C out is carry out and S is the sum. Now if you look into the block diagram of a 3-bit full adder, here you can see we are actually trying to add 4-bit with another 4-bit. So there are 4 full adder units. The first full adder unit is adding 2 bits A0 and B0 and considering a signal from carry in from the previous section. Similarly, the C out is now C in for the next section. Similarly, the C out from the second full adder is the input for the others, and so on. Now, from our previous discussions, we know that for a truth table of the full adder, where we have 3 inputs, the total combination is 8, and there is a sum and a carry. And if we get the output expression for sum in sum of product form, we will get an expression of this order, and if we get the sum of product expression for carry, we'll get, if we minimize the expression, we will get the carry expression as shown below. Now what we have to do is we have to implement this using a simple 4-to-1 multiplexer. Now it will be very easy if we use a 8-to-1 multiplexer, but using a 4-to-1 multiplexer we'll be able to in this particular lecture we'll be able to understand how a higher variable truth table can be implemented using a much smaller type of a multiplexer, and we can realize that using lower variable multiplexers also. Now let us see the truth table of a 4-to-1 multiplexer. As we all know, since it's a 4-to-1 multiplexer, there are 2 select lines, S1 and S0. So, and there will be 4 combinations, and when the select lines are 0 0, the input I0 gets selected at the output. Similarly, the other inputs are also selected at the output using the combination, using the select combinations. Now the output expression, we have already discussed this in the earlier lectures, will be is given as y equal to I0 S1 bar S0 bar, or I1 S1 bar S0, or I2 S1 S0 bar, or I3 S1 S0. So now if we try to realize the sum output, then we will have to consider the sum of product expression of sum, which we have already seen earlier. It was given C in bar B bar dot A plus C in bar B dot A bar plus C in B bar A bar, or C in BA. Now if we try to compare this expression with the original expression of the multiplexer, what we will have to do is we will have to somehow find out this four terms in this expression and replace the select lines using two variables of our full adder. So in this case, if we replace S1 with B and S0 with A, then if we rearrange this term, we can see that B bar A is similar to S1 bar S0, and in this particular expression I1 gets selected at the output, and so if we have a selection which is B bar A, then the input that is selected is I1, and in this case it is C in bar. So if we take an input called C in and invert that using a NOT gate and connect that to I1. So I1 is now having C in bar. So similarly, we'll have to find the next term and compare that with the multiplexer's equation, and in this equation we can see that the input is I2, and here the input is C in bar. So what we can do is we can just connect the output of the inverter to the I2. Here again we have C in bar. Now look at the third one, B bar A bar. Here the input is C in, and B bar A bar is similar to this where the input is I0, so we can directly connect C in to I0. Similarly, if we use this, the last one, C in BA, now it is similar to S1 dot S0, and here the input is I3, so we can put C in into I3. Now if we go for a rough test, what we can see is that if all the three inputs are 0, that means A is 0, B is 0 and C in is 0, then as per the expression it should be, sum should be 0, carry also should be 0, but we are only considering sum. So now if this 2 is 0, A and B is 0, obviously I0 is getting selected and C in is also 0, so output will be 0. Hence we can see that this particular section now starts functioning like a sum out. Now in the similar fashion we can go for the carry. Now in the case of carry, what we have seen earlier is we have got the expression C in bar BA or C in B bar A or C in BA bar or C in BA. Now in this particular expression you can see BA is common, so if we bring it towards this side, this particular expression now becomes 1 dot B dot A, that is 1 and B and A. Now the other term is C in B bar A. This is C in B bar A. Another term is C in B A bar, C in B A bar. The only term that is left out is B bar A bar. Since it's not there, if we expand this, we can easily write 0 dot B bar dot A bar. So we have got all the four terms as present here. Substitute S1 with B, S0 with A. Now compare the inputs. Now for S bar, S1 bar, S0 bar, the input is I0. So S B bar A bar, here it is 0. So what we have to do is we have to connect I0 with the ground. Now what about the next one? Next one is S1 bar S0. Now S1 bar S0 is similar to B bar A and the input is C in. So here the input is I1. So C in is connected to I1. In a similar fashion, if we check B dot A bar, here it is S1 S0 bar. So the input here is I2 and it is C in. So what we can do is we can connect I1 and I2 together with Cin. So this is how we can actually get the inputs corresponding to the expression. Now one more is left out, which is S1 S0. So here we can see it is I3 and here it is 1. So I3 is directly connected to plus 5. So again, if we try to understand whether it is working or not, we can substitute the values here. Suppose all the three input variables are 0, that is 0 0 here, I0 gets selected and Cin is also 0, but since the output has to be carry, so this is not sum, this is carry, so the output is to be uh, 0. So here in this case, if both the inputs are 0, and when both the inputs are 0, I0 is getting selected at the output, so I0 is actually connected to ground, so output will be 0. So what we can see is carry is 0. So in a similar fashion, if we try to analyze other combinations, we'll be able to see that the output is actually behaving like a carry. So in this case, we have a carry circuit implemented, a circuit which output gives us the carry of a full adder, and the previous circuit provides us the sum of the full adder. In this diagram, the sum has to be replaced with carry. So I would request my viewers to consider this as carry. Thank you very much for watching this video. I hope